Hey, welcome to this section. More on Matplotlib gems. In the previous section we explored the use of the right plots to understand data. In this section we'll first see how to draw barbs to visualize two-dimensional vector quantities. After this we'll learn to make a box and whisker plot, Gantt charts, error bars, and the use of text and font properties. Finally, we'll render text with LaTeX and understand the difference between PyPlot and Object-Oriented API. First, we move on to the first video of this section that deals with drawing barbs to visualize two-dimensional vector quantities. In this video, we're going to take a look at how to visualize two-dimensional vector quantities using barbs. We'll learn how to read barbs and how to visualize them using Python and Matplotlib. A barb is a representation of the speed and direction of wind, and is mainly deployed by meteorological scientists. In theory, they can be used to visualize any type of two-dimensional vector quantities. They are similar to arrows, but the difference is that the arrows represent vector magnitude by the length of the arrow, while barbs give more information about the vector's magnitude by employing lines or triangles as increments of magnitude. We'll explain what barbs are, how to read them, and how to visualize them using Python and Matplotlib. Here's a typical set of barbs. In this diagram, the triangle, also known as the flag, represents the largest increment. A full line or barb represents a smaller increment. A half line is the smallest increment. These increments are in the order of 5, 10, and 65 for a half line, line, and triangle respectively. The values here represent, for meteorologists at least, wind speed in nautical miles per hour, knots. We ordered the barbs from left to right to represent these magnitudes, i.e. 0, 5, 10 up till 100 knots. The direction here is the same for each barb and is from the north to south, because east-west speed component is 0 for each barb. A barb can be created using a matplotlib function from matplotlib.pyplot.barbs. The barbs function accepts various arguments, but we can also only specify x and y coordinates representing locations of observed data points. The second pair of arguments, u, v, represents the magnitude of the vector in north-south and east-west directions in knots. Other arguments that can be used are pivots, sizes, and various colouring arguments. A pivot argument represents the part of the arrow represented on the grid point. We get a pivot argument when the arrow rotates around this point. The value can rotate around the tip or middle, which are the valid values for the pivot argument. Because barbs consist of several parts, we can set up the colouring of any of those parts. So we have a few colour-related arguments that we can set up. Barb colour. This defines the colour of all the parts for a barb except the flags. Flag colour. This defines the colour of any flag on the barb. Face colour. This argument is used if none of the preceding colour arguments are specified. If any of the preceding colour-related arguments are specified, the argument face colour is overridden. The face colour argument is the one used in colouring polygons. The size argument specifies the relation of a feature to the length of the barb. This is a collection of coefficients that can be specified using any or all of the following keys. Spacing. This defines the space among the features of the flag or barb. Height. This defines the distance from the shaft to the top of the flag or barb. Width. This defines the width of a flag. Empty barb. This defines the circle radius used for low magnitudes. Let's now look into how to use a barb function by performing these steps. First, we generate a grid of coordinates to simulate observations. Next, we simulate observational values for wind speed. Then we plot barb diagrams. And finally, we plot quivers to demonstrate different appearances. So this is the complete code for our barb function, which will give you an output figure. Before we run it, let's understand how it works. To illustrate how the same data can bring different information to light, we used barbs and quiver plots from Matplotlib to visualize simulated observed wind data. Here we first used numpy to generate samples of variations for x and y arrays. Then we used numpy's mesh grid function to create a 2D grid of coordinates where our observed data is sampled at certain coordinates. Finally, u and v are wind speed values in the north-south and east-west directions in knots, i.e. nautical miles per hour. For the purpose of this video, we adjusted some values from the already available x and y matrices. We then divided the figure into two subplots, plotting barbs in the leftmost plot and arrow patches in the rightmost plot. We adjusted the colour and transparency of both subplots slightly, as well as turned the grid on for both subplots. Let's now step ahead and acquire some additional information. This is all fine on the northern hemisphere, where the wind rotates in a counterclockwise direction and the feathers point in the direction of low pressure. In the southern hemisphere, this is inverted, so our wind barb graph would not represent the data we're visualizing correctly. We have to invert this direction of feathers. Luckily, the barbs function has the argument flip barb. This argument can be one single Boolean value or a sequence of Boolean values such as the shape of other data arrays, when each item in the sequence specifies a flip decision for each barb. Let's now run the code to check the output. So, as we run this file, this code renders the two subplots as you see in the figure on your screen. Wonderful! In this video, we saw how to read barbs and visualize them using Python and Matplotlib. In the next video, we'll see how to make a box and a whisker plot.